So let's see the fundamental solution. Fundamental solution of an infinite beam on elastic foundation. Okay, I mean this is a it's an infinite long beam. Okay, with a point with a P loading. Okay, on a elastic foundation. Okay, with K and this EI. We call this kind of a green function or green solution because it's very important. This kind of a constant load can be used in the future for any kind of distributed load on elastic foundation. So this is very important, and we'll use this for finite lengths or somewhat. Okay, so this is first very fundamental solution, and now the next one will be with a concentrate moment. What the shape of this beam? Okay, so this is 2 times very fundamental solution for infinite beam. Okay. So let's derive the solution for this one first. Okay. So this beam, we can, because it's a symmetry problem, so we can change this problem to a beam to infinitely long, and here I have a half P, half P. Okay, actually this idea is like you take a very small pieces, and this is P, and this is a shear half P, and with a moment M0, and with this beam, this will be have a shear, and so this is what we have here. Okay, and on elastic foundation with K and this EI, and Q are 0. So we can directly use the homogeneous solution and with the boundary condition. So what is boundary condition? We have EI. Okay. Yeah. So we have what? We have a W EI triple prong at 0 equal to shear. So how much? This will be minus V, right? Minus V. So what is V? V here is positive or negative? For this end, positive V will be up, right? So this is minus P, happy. So this is happy. All right? And moment EI W double prime at 0 equals minus moment. And this is minus M0. Minus M0. No. Can we use this? Oh, we don't need. Suppose we need, right? No, anyway. But for this symmetry problem, we can use another property is a W slope at 0 equal to 0. Maybe we can use this and this too. Okay. And later on you want to find a moment once you got a W and the second derivative you can determine the internal moment. But for this one we can use this too. And with W, for this concentrated forcing at this point, and the diffraction at infinite should be 0. Because no function, too far. The energy is finite in local. To infinity, it should be 0. Nothing happened. Okay? And certainly the slope at infinity is easy, 0. Right? Certainly you can use the curvature or shear force 0. Yeah, but you can only use one of it. Yeah, okay. Anyway, so from this boundary condition, my homogeneous solution is exponential mu x C1 sine mu x plus C2 cosine mu x plus exponential minus mu x C3 sine mu x plus C4 cosine mu x. Okay. And okay. So since W infinity will be equal to 0. So this term will approach to infinity, right? So we have in force C1 and C2. You must be 0. Okay, otherwise your function cannot handle the condition when x approach to infinity. Okay, so C1, C2 has to be 0. So now my solution, my W equal to WH equal to exponential minus mu x. The C3 sine mu x plus C4 cosine mu x, right? And these two, C3, C4, can be determined by W slope at 0 equal to 0 and EI W triple at 0 equal to half P. Okay, half P. So from this one, I got a solution. I got a solution for this one. Infinite being with a P loading. Okay. Then my W x is equal to P mu 2k exponential minus mu x cosine mu x plus sine mu x. Okay, so this is my solution